Once again, today we're going to be working with a section or a chapter of exponents. We'll go through the idea of logarithms, the properties of logarithms, graphing of exponential equations, what's the graphs of the exponentials look like. If we take a look at e to the x, we want to include 3 points on our graph and get a graph of our function of e to the x. Well, the easiest way to put some values in here is put if x is equal to 0, x is equal to 1, x is equal to 2, what is your y value going to be? So you can quickly clack in your calculator, e to a power. Now, if you take a look at your ln button, that will get you an exponential. E is Euler's number, EULER. It's German. He's a German gentleman. Even though we're American, we're hooked on phonics, we would say Euler because everything that we pronounce is the correct way of pronouncing because we're Americans and everything we do is correct and we're always hooked on phonics. If you go over to Germany, EULER, it turns into an Euler real quick. So this is Euler's number. It's approximately equal to, it's like a value of pi. Pi we approximate to 3.14. Euler's number we approximate the value of 2.718. 2.718281828 and it goes on indefinitely. It's like the value of pi. It's an irrational number that will continue on indefinitely, never repeat, never terminate. So we are taking a look at Euler's number here to the 0 power, 1 power, 2 power. Well, if we take anything to the 0th power, we're going to get a value of 1. If we have an x value of 1, an x value of 2, we go an x value of 1, we have a value of 2.718. So we have 2.718, the value. If we square Euler's number, we have Euler 2.718 squared, or e to the x, or e to the squared, or e squared. What do we come up with? Come up with 8 point what? 8 point what? 7.389. And if I would take e to the negative 1, just so I'm going to know the number in here, if I would take the negative 1, once again, you can find your, if you go second button and go to your ln button, that's where you find your e to the x value. If we take e to the negative first power, what do we come up with? Here's what we get. 0.36. So we start to get a look at the graph of an exponential. This is a curve. We will be asymptotic. To the x-axis. We'll be asymptotic to the x-axis. Because we'll never reach a y value of 0. We'll just slide along that x-axis as we go along. And all of your exponential functions will look will have some sort of curve to it. Okay, this would be an exponential function. We might have, this is also called an exponential growth function. We can have one that is an exponential decay function where it would slide along there. So we'd flatten out the other direction. Well, if we want to use our ideas of translations, if I would add a -3 to this, this is a vertical translation. Okay, going back to our ideas of translations. We have a vertical translation of -3, which means every one of our points is going to go down 3 positions. So this point here will go down 1, 2, 3 positions here. This point here would go down 1, 2, 3 positions. This point would go down 1, 2, 3 positions. This point would go down 3 positions. 1, 2, 3. Our asymptote then would slide down 3 positions. So we would have a horizontal asymptote at y equals -3. So at this value of -3, we would be in a horizontal asymptote. If we subtract x from, or 4 from x, well, if we take a look, let's look at our graph of our function on the calculator. Let's go to our calculator. And let's go into our y equals. If you have functions that are there, you're going to have to clear them out. And let's graph second e to the x. Not sure what my window looks like, but if I would graph that, I need to change my window. There would be our graph of our e to the x. Well, in y number 2, let's graph y equals e to the x minus 4 power. So we have our second function, our ln, and let's go x minus 4 and close our parentheses out there. And let's look at our graph now. And what we would get is what type of translation? Horizontal translation. And that would be 4 units to the right. So we would have a horizontal translation of 4 units all to the right. So every one of my points here that I originally start with, I could go 1, 2, 3, 4 units here. 1, 2, 3, 4 units. One, 2, 3, 4. And 4 units here. We would still have the y-axis as our horizontal asymptote, but we would just have everything 4 units to the right. So once again, this is how we can look at the idea of translations to be able to help us out. Well, what would happen if we have e to the negative x? Well, graph y equals e to the x. What happens? E to the negative x. What happens with our graph? can be reflected about the y-axis. So we don't really have a translation, but we have a reflection about the y-axis. So my mirror image, I would have a mirror image across the y-axis. That would still be there. So I would just have a reflection about the y-axis. And once again, that going with what we did before with respect to our reflections, when we have f of x, then we go f at negative x, this reflects about your y-axis when you have that negative x in there. Then if we have a 4 and a 3 here, we would have a vertical translation is equal to 4. Our horizontal translation is the value that we're subtracting from our x. So we would have a horizontal translation of negative 3. So every one of our points, I know it's getting messy here, every one of our points, we would go up 4 and to the left 3. We would go up 4 and to the left 3. So if I take a look at every point, I would go 1, 2, 3, 4, up 4. Then we would go to the left 3, 1, 2, 3, and put our point in here. We would go up 4, 1, 2, 3, 4, and then to the left 3, 1, 2, 3. Up 4, 1, 2, 3, 4, and the left 3, 1, 2, 3. Then up 4, 4, and the left 3, 1, 2, 3. And that's where we can once again use our ideas of translations and our knowledge of translations to be able to assist ourselves. But it all starts with a base equation of e to the x, getting the equation y equals e to the x in there, and then looking at going up or down or left or right, or looking at translations and looking at reflections. If you look at the graph y equals 3 to the x, so we can go back to our graph function on our calculator, and I'm going to clear out my equations. If we look at the graph of 3 to the x power, so I have to go 3 caret x, and we look at our graph. Do we see much of a difference? No. If I would graph change the 3 to a 5 and look at the graph, do we see much of a difference? No. What's going to happen is going to skinny out a little bit. It will get a little steeper, a little faster. But all of our graphs are going to basically look the same when you look at your exponential function. It's going to be asymptotic to the x-axis, and then you're going to curve upwards. And that's what we call, once again, an exponential growth function. So all these translations here, it's going to all look the same. We're going to have a translation of, and the first one, what's our first one going to be? What would our what would be our translation in the first one? I have negative 2 plus 3dx. What would be our translation? Anybody? Vertical translation of -2. So all of our points would go up 2 positions. If I have y equals 3 to the x plus 2 power. Horizontal translation -2. Because it's what's being subtracted. That's x minus the -2. What's being subtracted there. Y equals x and negative x. That would be reflection. Y-axis. And the last one, what would be our translation in our last one here? 2 plus 3 to the x minus 1 power. Vertical translation of 2. Here's our vertical translation here. Here's our horizontal translation here. Whatever is being subtracted from x. Okay, so once again, if I get my base equation down and get 3 points down, I can then use my translation ideas to be able to find my graphs of what we have here. Solving exponential equations. I have 5 to the x is equal to 25. Now, I'm hoping that you could say that x is going to be equal to what here? 5 to the what power is equal to 25? Nolan? The second power. So x would equal value 2. But what we want to take a look at is a sort of different mindset to being able to to solve these equations. If I have a base of 5 over here. If I write 120, or not 125, if I would write 25 as a base of 5, how can we rewrite 25 as a base of 5? 5 to what power, Danae? 5 to what power is equal to 25? 2. So if I would write 5 to the x is equal to 5 to the 2th power here. Okay? What I'm doing is I'm rewriting our equations with the like bases. If my bases are equal, if I have a to the x is equal to b to the y, and if a is equal to b, if a is equal to b, what's going to have to be true about the exponents? They must also be equal. If a to the x is equal to b to the y, and if a is equal to b, then x has to equal y. Well, what I've done is I've wrote these as alike bases. So I have 5 to the x is equal to 5 to the 2nd power. If my bases are equal, which is what I'm trying to get, then my exponents must be equal. So if I look at 5 to the x is equal to 1 over 125. Let's just take this slow here, and let's take a look at 125. How can I rewrite 125 as a base of 5? 5 to what power? 3rd power. So I have 5 to the x is equal to 1 over 5 cubed. But I'm still not in this form where I have this is equal to this. But I have 1 over 5 to the 3rd power. Well, how can I write this and take this up to here and get it out of the denominator. Now this is our knowledge of exponents. How can we rewrite 1 over 5 to the third so I just have 5 to some power? What can we do? Once again, we're knocking on our brain from algebra. Anybody remember? There you go. Winner, winner, chicken dinner. If I have x to the negative a, this is 1 over x to the a power. Or if I have 1 over x to the negative a, this is x to the a power. The negative exponent reciprocates our base. Whatever our base is, it just reciprocates. So what we are left with is 5 to the x is equal to 5 to the negative third power. Now I have a like basis. If I have a like basis, the exponents must be equal. So x must equal negative 3. This should be to the x power up here. It's not 625x. So if we look at 5 to the x minus 3 is equal to 625 to the x power. And we want to solve for x. First thing, once again, we want to write as a like basis. So let's look at the 625 because that's the bigger one. Can I write 625 as a base of 5? Right? 5 to the fourth power. Once again, go slow with this. So we have 5 to the x minus 3 power is equal to 5 to the fourth to the x power. Okay? All I've done is I rewrote 625 as 5 to the fourth power. 5 to the fourth power is 625. Now, once again, we have properties of exponents. On the right-hand side, we have 5 to the fourth to the x power. So we have a power to a power. When we have a power to a power, what do we do with our exponents, Brendan? Multiply them. So this gives us 5 to the x minus 3 is equal to 5 to the 4x power. When we have a power to a power, we multiply our exponents. Once again, we are kicking cowbells out from algebra. Okay? Exponent rules. I have a like basis here. If I have a like basis and I have equality, that means my exponents must be equal. So x minus 3 has to equal 4x. If bases are equal and I have equality there, the exponents must be equal. Now I got an equation to solve. I can subtract my x. So solve your equation. Subtract your x. And divide by your coefficient. So x is equal to negative 1. Rewrite 125 as a base of 5. Once again, keep it to the exponent of x. Don't try to do many things at once. Should have a 5 cubed there. We then have a power to a power. Using your definitions of properties of exponents, power to power, you multiply them. and then solve the equation. James, what do you get? What do you get? Oh, that's a 6, my bad. So x is equal to negative 3. Subtracting your 2x over, or subtracting your x over. So we have negative 6 is equal to 2x, divided by 2, x equals 3. Solve the next one. 2 ways of dealing with the next one. See what you see. Check your answer with somebody around you. Jacob, what do you come up with?
9 to the second power times x.
Hmm?
What the answer? I got
Yeah, what's your answer?
2.
2. X equals the value of 2. Go with that. We have 9 to the x plus 2 is equal to 9 squared to the x power. So we have x plus 2 is equal to 2x. So x equals the value of 2. Solve the last one. How do you deal with a square root? What exponent do we have with a square root? Anybody remember what exponent we have with a square root? I'm okay with this, but what exponent do we have with a square root? Nobody remembers. 1/2. Once again, we are taxing your properties of exponents. If I have the 8th root of x, of x to the b, whatever the root is, and we have x to the b, this is equal to the x to the b over a power. This is your denominator. Bless you. This here is your numerator. Where? It's perfect for the exponents. Okay, so this is your numerator. This here is your denominator. Well, if I take a look, I have an exponent 1 here, and if I'm taking the square root, it is understood to be a 2 there. So I have 5 to the 1/2 is equal to 5 to the 3x. So we have 5 to the 1/2 is equal to 5 to the 3x. Exponents are equal, then the bases are equal. Or if bases are equal, the exponents must be equal. So we have 1/2 is equal to 3x. Dividing by 3 is like multiplying by 1/3. So I have 1/2 times 1/3. So we have x should equal 1/6. A little bit of a review of exponential ideas. Tomorrow we'll get into the meat and potatoes of logarithms. Monday we'll deal with properties of logarithms. Once again, we will whirlwind tour this through the idea of logarithms. Okay. Saddle up and hold on. Sorry. Giddy up.